everyone, and welcome to screencast number 3 on Chapter 21, New Renewable Energy Alternatives. So we left off talking about active solar energy collection, and I wanted to take a look at this picture and go through this solar collector to tell you how it provides heating. So here is the flat plate solar collector. It's made out of metal and glass and typically has water that runs in between. So the sunlight is going to shine on this flat plate and warm the water that is inside of there. The collector then senses when the collector is warm enough, and the pump will actually switch on, and that will circulate the fluid through the whole system. So as the water warms, it'll then go into a tank, this heated tank that you see here, and it flows through this tank where the pipes will then transfer the heat water. The heat water could go into a boiler that heats the water needed when the solar energy is not available. The cold water supply is what comes in through the buildings or the house. So this is how this solar panel would work. All right, so now we're going to look more at what would happen if we concentrated the solar rays and magnify the energy. And I think probably you've all played with a magnifying lens at one time or another, where you know that if you angle a piece of glass or a lens just right, that it condenses the light on a spot, and you can easily burn a leaf or burn a hole in wood if you hold it there for a long enough time. So we can do the same thing with the solar energy that's coming down in large amounts, and we can intensify this. This is actually called a solar cooker, and it's very simple. It's a portable oven that uses reflectors to focus sunlight onto food so that people are able to cook it. This has become very useful in the developing world. So I think here's a picture of what a solar cooker would look like. They've been able to make these a little bit more portable than what you would see this one being. And you can put your food in here, and that energy just heats up. It's collected in these mirrors in this disc, and it will heat up whatever you have. So it doesn't require any electricity to heat it. Now, as I said, they've been able to make these smaller and more portable, and there's a lot of countries in Africa that are using those. Okay, let's go back a minute, if it allows me. So, it didn't. All right, so moving on from that, utilities are using the principle behind solar cookers to actually generate electricity. They are being harnessed in things called a concentrated solar power, or CSP, and this can be harnessed by several methods. We see it happening in sunny regions in Spain. In the U.S. Southwest is also using these. The dominant technology so far is a parabolic approach using a trough in which curved mirrors focus sunlight onto a synthetic oil in the pipes, and then that superheated oil is piped into an adjacent facility where it creates steam, and it drives the turbines to generate electricity. So let's go back to this picture, and this would be the concentrating solar power, the CSP. And here's the troughs that you're going to see that are placed within these strategic locations, and as they heat up the oil that's in there, it's taken to a tower or a place where it can be absorbed and held and then used later to fuel the turbines. Okay, so let me go ahead. Sorry, I thought there was more from there. Another thing that we could use is numerous mirrors, and we'll go back and we'll take a look at that picture that can concentrate sunlight onto a receiver atop a tall power tower. From this central receiver, heat is transported by air or fluids, sometimes molten salts, and these are piped to driven generators to create electricity. So let me go back to that picture again, and this is where you're getting these massive solar panels that you can get. This is what we see in this picture here, where it's going to a central tower, and then it can be used to drive steam generators to create electricity. The CSP facilities need to be located in sunny areas. So that's one of the drawbacks, but we've got a lot of sunny areas available. The Nevada desert could generate enough electricity to power the entire U.S. economy. So that's tremendous. The International Energy Agency estimated that just 100 square miles of the Nevada desert would be able to do this. It could fulfill 1/4 of the global electricity demand by the year 2050 if we step up the investment. German industrialists and investors have spearheaded a very ambitious effort to create an immense CSP facility in Africa's Sahara Desert. It is a $775 billion project that they're called Desertec. And thousands of mirrors are being spread across the vast area of the desert of Morocco, and they would harness the Sahara's sunlight and transmit electricity enough for Europe, the Middle East, and North Africa. There are some people, however, one of them is Hermann Scherer, that say it would be vulnerable to sandstorms, political disputes, and it would be less reliable and more expensive than decentralized production from rooftop panels that feed-in tariffs are promoting in Europe. So many people, are growing wary of the environmental impacts that such large-scale developments may pose. So that is one of the drawbacks. Here is a picture of the troughs that I was mentioning to you. So this is called a solar power farm, and it requires large areas of land, and it exerts some substantial environmental impacts. Just look at the scale of size of these. Those are 3 men or women, can't tell at this angle, that are walking in between, so you can see just how huge these are. Researchers estimate that the impacts are less than those demanded by fossil fuels, and they say that burning coal for energy uses at least as much land, once one includes the strip mining needed to obtain the coal. The solar plant here in Kramer Junction, California, is just one of 9 that's spread across more than 1,600 acres of the Mojave Desert, and it provides power for over 230,000 homes. Please make sure that you read the story behind the scenes on page 592 and 593 that coincides with this picture. Okay, in the last 5 minutes of the screencast that we have, we're going to talk about photovoltaic voltaic cells that generate electricity directly. So we call these photovoltaic or PV systems, and these are cells that convert sunlight energy by making use of the photovoltaic effect or the photoelectric effect. This effect occurs when light reaches the PV cells and strikes one pair of plates made primarily of silicon. We're going to take a look at this in a picture in just a minute. The semiconductor of silicon conducts electricity, and then the light causes one plate to release electrons, which are attracted by an electrostatic force to an opposing plate. Connecting the two plates with wires enables the electrons to flow back to the original plate, and it creates an electric current. This current is referred to as a direct current, or a DC. This can be converted into an alternating current, and this is what you're more familiar with, which is an AC. And this is used for residential and commercial electrical power. That's why I said you're more familiar with it. Now, small PV cells may already power your watch or your calculator, so you've probably seen them on your calculators, more than your watches, I think. We can see them atop some rooftops at homes and other buildings you might have passed and seen. The PV cells are arranged in modules, and these comprise of panels. So the picture that we saw in the very beginning of this chapter is one that shows the photovoltaic cells. Researchers are currently experimenting. Before I even get into that, here's the picture of those cells. Okay, this is what an actual panel looks like. So each one of these sections would be considered a module, and these modules are all connected so that you can see here. The sunlight is actually going to hit those silicone layers of the cell, and the electrons will then be knocked loose from some of the silicon atoms, and they tend to move from what is called the boron-enriched or P-type layer toward the phosphorus-enriched N-type layer, and they connect the two layers wiring, and this remedies any sort of imbalance as the electrical current flows from the N-type layer back to the P-type layer. This direct current is converted into the alternating currents to produce usable electricity, and the PV cells are then grouped in modules comprising of the panels that you just saw, and can be erected in different arrays in the direction of the sunlight. So researchers are now experimenting with thin variations of the PV technology. This is called thin film solar cells, and they're using photovoltaic materials compressed into very ultra thin sheets. The thin solar cells wind up being lighter weight, far less bulky than the standard crystalline silicone cells that we've seen in the pictures. They're not as efficient at converting sunlight to electricity, but they're a little bit cheaper to produce. So the technologies they're thinking could be incorporated into roofing shingles and potentially many other types of surfaces, even highways. And people are looking at these solar technologies as being promising for the future. These PV cells of all types can be connected to batteries to store and accumulate energy and charge it until it's needed. We see that with our calculators. And producers of the PV electricity can sell their power to their local utility if they connect to a regional grid. So parts of 46 U.S. states, the homeowners are selling their power to utilities in a process called net metering, in which the value of power the consumer provides is subtracted from the consumer's monthly utility bill. The feed-in tariffs that we've talked about in Germany are taking this a step further by paying the producers. We're almost done, so we'll end this screencast and continue on the other side.